everybody here in the audience and on Facebook Live, and welcome to another edition of Sci-Café. Today our topic is Earthshaking Events, carrying on from last month's topic, which was about extreme environments in the Red Sea. But this topic today is a little bit interesting in that I think we all know about volcanoes growing up. We saw them in magazines and on TV and everywhere when we're growing up. We know about earthquakes. We kind of know about plate tectonics. These are things we hear about even as kids, but I don't think we ever fully stop to think about them, to think about the timescales, to think about how impactful some of these earth-shaking events are. So we have three panelists today that are going to address some of these in more detail and teach us all a little bit about this topic. Just to remind you about the format, I'm going to ask a few questions of the panelists. This will probably take about 10-15 minutes. And then the real fun of this event is to open it up to you to ask questions once you understand the expertise of each of these panelists. So please, in about 15 minutes, be ready for me to toss you the microphone and for you to ask a few questions. So I'll start by having each of the panelists introduce themselves and just say a little bit about their expertise and how they got into this particular field of study. So maybe you want to start?
Okay, thanks. I'm Abdulkader Afifi. I'm a new professor at KAUST. My field is geology. And I started my life as a hard rock geologist, which is studying the Arabian Shield and looking for mineral deposits. And then I joined Aramco and reinvented myself as a soft rock geologist looking for oil and gas. I spent 28 years, and now I've joined KAUST. And doing research and teaching in my field.
Fantastic.
Yeah, my name is Sigurjón Jónsson. I come from Iceland, so that's the land of active volcanism. I kind of grew up with volcanoes in my backyard. Only 20 kilometers from my home, during my childhood, a volcano erupted 10 times. So more or less could see it from my bedroom window as a child. So I guess that definitely was one of the main reasons I ended up in earth science and started to study geophysics. And I focus on processes, active processes related to earthquake activity and hazards, as well as volcanic processes, and sometimes the interaction between earthquakes and volcanoes.
So my name is Ibrahim Hoteit, and actually my background is in mathematics. I did my bachelor in pure math, then master in applied math, and PhD on developing new methods for efficient forecasting. Back then, when the satellites were launching satellites to observe the ocean, and the oceanograph were excited about building forecasting weather systems, like for the atmosphere. So I worked on that during my PhD, and then I moved to Scripps, where I learned also more ocean. We worked on the Pacific, reconstructing the circulation of the Pacific, on the problem of oil spills in the Gulf of Mexico, and the Mediterranean ecosystem forecasting. And then when I moved to KAUST, we started working on the Red Sea. And then this is when we learned that we need the atmosphere, and not like in other places where we have meteorological centers. So we started also working on the atmosphere over the Red Sea to first the ocean. And now I'm working with a group on every aspect of the circulation of the Red Sea and on the atmospheric circulation on top of it.
So just to follow up quickly on that, how do those simulations relate to large events, earth-shaking events? How are the two connected there?
Yeah, okay. One of the very recent examples I can give you, we have a paper in 2018 in Science Advances, in which we suggest, and actually we show, that the Red Sea gets ventilated every once in a while, and one of these two of these ventilation events were caused by volcanoes eruptions. One in the Philippines, the Pinatubo, and one in Mexico, Chichon. So what happens, these ashes reduces the temperature and create a very large anomalies, strong anomalies of temperature in the northern Red Sea. The water becomes heavy, cold, it sinks, and when it sinks, it flushes all the deep water down, and this ventilates the whole Red Sea and changes the whole Red Sea circulation, and it's caused by volcanoes. This is a very quick example.
You said that was close. I don't picture the Philippines and Mexico as all that close to the Red Sea.
It's not that close, but dynamically close. The measure is not by distance.
Yes.
There is statistical distance. This is dynamical distance, and dynamically it just created an anomaly in the northern Red Sea.
Yeah.
And it's very important because it brings oxygen down, and it's kind of an extreme event for the Red Sea itself. It's not for the humans.
Yeah.
But for the Red Sea, it's an extreme event where you have like a rock, putting it in the water and flushing everything out.
Very cool.
It was pretty cool.
All right, so I'm going to try and put, for lack of a better description, boxes around each of these people. So, Professor Afifi, maybe you can say a little bit about kind of the tectonics and the larger global movement that happens.
Well, the most earth-shaking events, when people say earth-shaking, they think of earthquakes, and to a lesser extent, volcanoes. Both are a product of the fact that we live on a planet that is moving, not only through space, but the planet is, the surface of the planet is composed of plates, and those are moving past each other, sometimes colliding, sometimes slipping horizontally past each other, and sometimes moving apart and creating new crust in between, which are the oceans. And so each of these plate boundaries are sites for where rocks are moving past each other. And rocks can move smoothly past each other, a process called creep, or they can stick because of friction, for example, or bends in the fault surface that separates them. And so when they stick, stress builds up in the rocks. It's like loading a spring. And that builds up to a point where the stress overcomes the friction, and the rocks move fast. So they could move a number of meters in either up, down, or sideways. And that generates an earthquake. Mm-hmm. And that is called a rupture. And an earthquake is simply the waves of compression and up and down that go through the earth. And on the surface, you also generate, and that's the shaking that people experience. So those are the common earth-shaking events. Also, the other way you make earthquakes is magma is rising through the crust from, say, a depth of 60 kilometers to the surface where it erupts as a volcano. And in the process of working its way up, it breaks the rock, pries them apart. A process similar to fracking that's used in the oil industry. You just increase the pressure until you split the rock. Mm-hmm. So magma comes up, and each split is another seismic event that, if strong enough, can generate an earthquake. I should mention here that the biggest the biggest earth-shaking events are when rocks from space collide with the Earth. Okay? And we experience that simply as meteorites. But in geologic time, some large planetary or asteroid-type objects, say 10 kilometers in diameter, have crashed into Earth. Now, to some extent, the atmosphere burns them up on the way down. But if they're large enough, they don't burn completely, and they collide with the Earth at very high velocity. Those are truly earth-shaking events. They make the planet ring. Yeah. They stir up a lot of dust that changes the weather, the climate, and it causes mass extinctions, like the famous Chicxulub impact near the Yucatan in Mexico about 65 million years ago caused the extinction of not only the dinosaurs, but something like 90% of life forms. So those are the biggest earth-shaking events, and luckily we haven't experienced those recently.
So, Professor Jónsson, you cover two of those areas in particular, the earthquakes and the volcanoes. So let me make it specific to KAUST. Is there earthquake activity close to us here on the Red Sea, and is there volcano activity close to us here?
Yeah, I guess Saudi Arabia is probably not a country that comes to mind when we think about volcanoes and earthquakes. And it's not a very hazardous place with the, if you think about these type of hazards, although it is somewhat significant, we should not ignore it. And so if you just think about volcanic activity, like we were talking about, Abud was talking about these plates moving apart, moving towards each other. So the Red Sea is a spreading center. It's moving apart about 1 centimeter per year, so somewhat slower than your nail is growing. And it makes room for new material to come up. And from time to time, we have things that we call rifting events or rifting episodes in the central part of the Red Sea. It's about 100 kilometers away from here, the closest portion of it. And in the past, most of these events have gone unnoticed because these are volcanic eruptions at the bottom of the seafloor at 1,500 meter depth or 2,000 meter depth. So most of these events in the past hundreds of years, we have simply not known about. In the southern part of the Red Sea, on the other hand, it's a little bit shallower. So sometimes these eruptions make it to the surface. And just in the last few years, we witnessed some astonishing events, which included formation of 2 new volcanic islands in the southern Red Sea. And this is quite rare to witness around the planet, to see new islands actually form. Only a handful of those, or half a dozen in the past 100 years, have actually been formed. And 2 of those happened here right in front of us, but in Yemeni water, so it has been a little bit difficult to go to observe them in person. So most of the things we know about these new islands are from Yemeni fishermen and from remote observations from satellites. And so this is one thing that we have been looking at. And then volcanic hazards inside Saudi Arabia are also can happen from time to time. Medina, for example, is at the edge of a volcanic field that had a significant eruption a few hundred years ago, and this is something that could happen again. And earthquakes, luckily for Saudi Arabia, are relatively rare compared to many other parts. Okay, we have many in the middle of the Red Sea, but they're not that big. So the largest events we can have are typically on the edges of these tectonic plates, and they tend to be larger and more frequent in the countries around Saudi Arabia than in Saudi Arabia, although from time to time we have some events that we need to. And one thing we do in our research is to study those events that happen, to try to see what processes were involved, and also to learn more about, okay, how frequent and how large could the events in the future be, to basically prepare, to recommend, I mean, how should we build to withstand these kind of events. And it turns out, for example, 2 major construction projects that are taking place in the kingdom now, the King Salman Bridge that is going to link Saudi Arabia to Egypt, going over the Strait of Tiran in northern part of Saudi Arabia, is exactly in the area where we have the largest earthquakes in Saudi Arabia. And Neom is also in that area. And we need to, therefore, put special focus on this area to try to understand, okay, when did we have the last huge events? What is the frequency of these big events? What kind of level of shaking can we potentially have? And where are the vulnerable areas? So these are kind of things that we are looking into.
Good. Okay, and I'm assuming when things shake in the Red Sea, that causes movement of the waters as well. So is this something you guys study, Ibrahim, with simulations?
Yeah, we looked a little bit at the history of tsunamis in the Red Sea, and there was actually, don't quote me on the exact date. There was one. We picked the largest one, and we simulated the water level, tsunami level during that time, and we didn't reach more than 40 centimeters, 50 centimeters. So it wasn't that large to make a story out of it. But yeah, we do some research on methods to predict tsunamis on time, to allow us to predict tsunamis from satellite data on. But this should be, the method should be very quick, so that you can provide the information on time before it happens. This is the whole difficulty.
So why would somebody like KAUST, or why would anybody want to know about the movement of the water, the tsunamis that are on the Red Sea? I mean,
everyone should. In the Red Sea, you want to know if there are areas at risk of tsunamis. So if you tell us where are the areas at risk of earthquakes, and what kind of movement we should expect, we can take these, put them in our models, and project where the areas at risk of high water levels.
Yeah.
Even half a meter might have an important engineering impact on the design of a new city or a new harbor, a new.
Have you worked on some projects like that?
We worked on tsunami was not part of the assessment we did, but they were interested in the highest waves that might strike them, cake actually.
Okay.
Our cousins, and they were building the lagoon, and they wanted to know the highest water levels that they can expect from.
So they're constructing this massive city, and
yes.
they need to know how high above.
Yes, and
sea level
accordingly they
building.
can protect the lagoon and the waterfront. And they were planning for 4 meters defense, so they need to import 4 meters of sediments to bring the city higher, and then this was projected to be around 4 billion riyals, 1 billion riyal per meter. And then when we did our calculations, the extremest we've seen in waves height was about 1.2 meters. So they reduced their projections to 2 meters instead of 4, and this saved them 2 billion riyals just from the data of a PhD student who was doing it as part of his PhD.
Very cool.
I should have negotiated better.
1%. That's what you need, right?
1%.
All right. Be thinking of questions. I'm only going to ask 1 or 2 more, and then it's on you. Professor Jónsson, maybe you can say something about how you start to study up near that Neom area, and what type of input can you provide? Like Ibrahim is saying for cake, what type of input can you provide on the earthquakes to help with the development?
Yeah. So we started working up there a few years ago, actually before the Neom was decided, before the bridge was announced. So that kind of, when these things were announced, it did put hugely increased importance to the work we were doing. Now, when we are studying hazard, we need to find out where earthquakes happen, how large, how frequent. And to do that, you apply multiple different methods. One thing that is important to know is what happened in the past. And it's a plate boundary that is relatively slow. It's moving maybe some 5 millimeters per year, which is very little. If you think about the San Andreas fault, it's about 5 times or 6 times, 7 times faster than this. And also in Turkey, it's moving faster, it's more active. So when the plates are moving faster, then you have more frequent of these large devastating events. So in Gulf of Aqaba, it's only about 5 millimeters per year, which means that typically there can be hundreds of years between large events. Further north, we have historical records from Syria and Jordan and Lebanon for the past 2,000 years, but closer to the Red Sea, there was always less of a documentation, less population, so we don't know much. We know there was a big earthquake in 1588, but we don't know where it happened. It was felt in Medina, it was felt in Cairo, so its influence was enormous. And there was another event about 500 years earlier in 1068. Again, we don't know where it happened. And initially, scientists put it somewhere kind of at the center of where the shaking was kind of mapped from very limited documentation from these old times. Now we think they happened on that plate boundary in Gulf of Aqaba, but we don't know exactly where. Maybe at the location of the King Salman Bridge, which is supposed to go right over this plate boundary fault. So you need to figure out, okay, if you have a magnitude 7.5 earthquake right at the location of the bridge, how are you going to design that bridge? That's an engineering challenge. And we don't have, around the world, we actually don't have many examples, actually only one that I can really think of, where you have a major bridge crossing a plate boundary.
I'm guessing this is in my home state of California.
No, it's in Turkey.
Really?
New bridge in Turkey. So in the San Francisco Bay, they're all kind of not crossing the fault. They're close to the fault, but they're not crossing the fault.
Got it.
So this is what can you do when you don't have historical accounts? So we took the KAUST ship up there a few months ago, and we lowered a coring device to get kind of tens of centimeters, a meter scale, just from the sediments, and see, okay, what do the sediments of the bottom of the sea tell us? And interestingly, there are evidences for major events, whatever they are. So sand in the middle of the ocean that should not get there unless there is a major shaking or collapse. And we are now in the process of dating these things and trying to figure out, okay, where these major events happen. Do they correlate with 1588 and 1068? And was that at the location of the bridge or further north or further south and things like that? So these are one thing they're trying. We are also looking at other things to learn about the activity there.
Very good. I think that's probably enough of us talking. What do you want to know about earthquakes, volcanoes, developments? Yes. Here.
It's a really very interesting topic, and it's rather a question to you, John.
Yeah.
What is KAUST doing in terms of providing a long-term monitoring of the seismic activity? I know that NEOM site has been chosen, but is there any seismic observatory to monitor the conditions in the region for some period of time so that you know what you need to do?
Yeah. I'll actually defer because I'm guessing you two have some information on that.
Well, the Saudi Geological Survey, which is a national institution based in Jeddah, they have a national network of seismometers, over 100 instruments distributed all over the country. So they do the day-to-day monitoring, and we collaborate with them from time to time. And then if there is a special hotspot that we want to monitor, then people at KAUST have some extra instruments to put into that area, and then they often work with the local scientists as well. So there is an entity, like in most countries, that puts in just like weather monitoring, they report online when there's an earthquake. You can actually go to their website and see where the latest earthquakes were and so on.
And from a Red Sea perspective,
Yeah,
especially up near NEOM?
So KAUST is initiating the NEOM Center of Excellence, and part of it are discussions. We're still in the discussion to put a proposal for monitoring the ocean atmosphere circulation and also biology in the Red Sea. Mike is part of it as well, and hopefully this should start in the next semester or so.
Yes,
Thank
maybe
you.
you can toss over there.
So my question is with Dr. Hoteit. So what do you see the role of visualizations in analyzing these earth-shaking events?
So she has that typical question from a visualization person.
Can I broaden that a little bit? I mean,
Sure.
I want to hear the answer
please,
to that,
please,
but in general, I if you can give people an idea, like simulation. So you put all this data into the computer.
Yes.
And how does that? How is that? How close is that to reality? How can we use that to predict? I think there's this disconnect. When I think of you putting all this data in the computer, I don't fully understand how that leads to an output, whether it's visualization or action.
Actually, all the data comes out of some of the computer. But again, we put as much as we have, and as you imagine, in the ocean, in the atmosphere, we have much more data than the ocean because satellites can see the whole column. And in the ocean, the satellite can see only the surface, and how to see down, then it becomes much more complicated. There are like Professor Jones at KAUST who use gliders, underwater vehicles, but you cannot observe the whole Red Sea. And imagine only the Red Sea. It's a small basin. It's a very small basin. You cannot observe all of it. So what we do, we take all the possible information available, and likely we understand quite well the dynamics, the physics of the circulation. The Navier-Stokes equations are there to help us. If we know what's going on now, we know what's forcing the ocean, we know the bathymetry of the ocean. If everything is perfect, and we have a bigger supercomputers than Shaheen, we should be able to simulate what's going on.
Mm-hmm.
We should reduce the uncertainties, but this never happens. So what we end up doing is, we simulate the ocean, but we start taking data that are coming as we go from satellite, whatever data available. We merge them together, combine them to make the best possible forecast. This is why when you do weather forecast, for instance, you can, if my wife tells me, look, we cannot travel, this week will be very bad, I tell her, don't look at next week. Tomorrow we trust it because we have data in it. 3 days, okay. 1 week after, because, there are uncertainties in the system that can drive, our models can drift because of these uncertainties. This is where incoming data will always be useful. But models are getting better and better. With history also, with the with history in time, we can not only validate but also train our models to become better and better. And supercomputing is becoming also, and we're having more and more data to put it in, so we get more accurate forecasts. So,
and I think that's where the visualization question comes from.
And so with the visualizations, then we have all these tons of data that comes out, and then it's not only a challenge for us, but challenge for the users. Like you want to do something on extreme, and the users are not the scientists. Users are the standard population, but also the people who are the policymakers, and they have to make a decision. So they need to visualize this data, and visualizing this data might be complicated. So visualization is look at it as the interface, as a very important interface to be able to visualize our data in a way that is comprehensible, because we're talking to terabytes and petabytes of data that cannot be moved around and handled by simple people. Visualization, I can assure you, it's a very important component.
Other questions? I want to follow up with Professor Afifi. So we didn't talk about geothermal energy, which is kind of related to this earth shaking. Is that something that is here in Saudi Arabia? Is that something that could potentially be tapped?
Yeah, a few years ago, I led a project within Aramco to evaluate the potential of Saudi Arabia for geothermal energy. And there's conventional geothermal energy, which is what they have in Iceland, where you have a heat source that's pretty much a point source, magma rising under a volcano. When that happens, when you have oftentimes a shallow magma chamber at a depth of, say, 1 kilometer, and the magma is at a temperature of 1200 degrees centigrade. It's molten rock. And so you have circulation of groundwater, and typically it sets up a convection cell, recharged by rain from above. Water goes down into the rock, gets heated, and comes up. And the surface manifestation of that are things that a lot of you have experienced: geysers, hot springs. Okay, so that is conventional geothermal energy. You drill wells into what is like a hot reservoir, and ideally you would produce steam, dry steam, temperatures because that contains the highest enthalpy. And that's usually taken straight into turbine, spin the turbine, and then there's ways to extract more energy. In Iceland, in fact, hot water is used. That's a product of the geothermal energy, is used to melt snow off the street and as a domestic hot water source. So in Saudi Arabia, the volcanoes are there, the volcanic areas. One problem we have is aridity. We don't have a lot of rain. It's a desert. And so, we have concerns about whether you have, there are some places in the coastal plain where there are hot springs. So the engine is working, but we're not assured that the engine is working as efficiently as it would in, say, the equatorial regions where there's a lot of rain, or the northern hemisphere. So that is a concern. And finding geothermal energy in the volcanic source geothermal energy is an art by itself. So there are people who are specialized. They run electromagnetic surveys because knowing where to drill is very important. What I'm excited about is not that kind of geothermal energy, but what I call low enthalpy or unconventional. It's basically, it's no secret that as you go down, things get hotter. This is just a normal heat flow from the Earth. And the average heat flow is about 35 degrees centigrade every kilometer. So if you go kilometer beneath us, ambient temperature is 20, so Add 35 to that, that's 55, and then, and so on. And it turns out there are technologies now that have not been tested, but instead of using the hot water to drive turbines and generate electricity, you can use it to do two things that are needed for this country. One is desalination, the energy source for desalination, so you can do this along the coastal areas. And the other one is district cooling. So you can use the hot water as the energy source to cool. And typically you need communities that are set up for district cooling. So basically there are off-the-shelf instruments that convert the heat from the water, the energy from water, into a chilling cycle. So, and that can be used for district cooling, and that is also needed here. Yeah. Perhaps not for base load, but for the hottest days in the summer.
Got it.
And so I think there's both are of significant potential in the country, both along the west coast, which is the Red Sea coastal plain, as well as along the Arabian Gulf Coast. And we're going to start some research here to try to make it happen all the way to a pilot plant stage.
Very cool. What other questions? Yes. Where's the... She's got a microphone here.
Okay, I guess it's a question for all three of you. Based on your research and the way you experience the Earth activity at the moment, do you expect any earth-shaking event anytime soon?
You mean here?
In general, in the world. I mean, in the whole planet.
Ah.
Should I?
Open-ended question.
Where that could be.
Yeah, I mean, super volcanic events luckily are very rare, but their impacts are great, and it's all kind of an interconnected system, such that it has an influence on climate, influence on the oceans. We have earthquake, volcano interactions, and so on. Large earthquakes that come from time to time. I mean, and they don't have to be so large to be devastating. So the impact can be huge, even though the earthquake is not that big. When we guess the most recent example is an earthquake in Indonesia that was big, but a moderate size, and seemed to have triggered a landslide-driven or submarine landslide-driven tsunami that killed a lot of people. So we are learning more and more about where earthquakes happen and how big they can be, but for short-term warnings, many people believe they are not possible. Other people say, well, we don't know how to predict them well yet. And then a small group says, well, we can predict them. But not many people believe them because they haven't been that successful.
So let me jump in on that, because he's using a supercomputer and predicting 40-centimeter tsunamis. So that seems to be pretty accurate. But how come we can't pinpoint earthquake? I mean, we understand the physics, right? So why can't we pinpoint some of this?
Yeah, the onset is, some people think it's intrinsically just a random process. So it's the start of it. We know more or less. I mean, people think, okay, if an earthquake starts, you can detect when it begins. Is that earthquake going to grow large, or is it just going to be one of the small ones? And some people say, well, there's no difference between the initial onset of an earthquake. Therefore, it just is very, very difficult. And then what happens before? Is there any kind of preparatory process? So this is very different from large volcanoes, for example, or volcanic activity, is that we know more and more about the preparatory processes before volcanic eruptions. And where volcanoes are well monitored, you can actually give out useful warnings. And I know in Iceland, for example, where volcanoes are monitored quite closely, if you look at the past 40 years, there have been about 25 volcanic eruptions in Iceland. 2/3 of those had a public warning issued, such that they were, in some cases, evacuation, some cases, warning. So 2/3 out of, that's pretty good, and not too many false warnings. So we don't have that success rate everywhere in the world for volcanoes, because volcanoes are not that well monitored. There are about 1,000 of them active, which are not under the sea, and many of those are relatively poorly monitored. But we are improving on this front. So, yeah.
Well, the short answer is it's certain that because the planet is a live planet and plates are always moving, that there will be volcanic eruptions and earthquakes somewhere. I think in the predicting earthquakes, say on the horizon of days or hours, is not going to be achieved anytime soon. We know why earthquakes happen. We know the faults. We can map the faults where the earthquakes are going to happen. But where along this line on a map the next rupture is going to happen is very difficult. If an earthquake happens on a fault and releases a lot of energy, then you know that it's not going to happen at the same location anytime soon. You have to go somewhere else where the rupture hasn't occurred and the energy has been built up. So in some places, having a fault at a certain location tells you that it's not going to happen for another 1,000 years, for example. Okay, but further along the fault, and then so you can tell why. You can tell along a line where, but you cannot tell when. That part there are very few signals that you can monitor for that. The good thing, though, that people are doing in Japan, for example, they have a network of seismometers all over the country. So if an earthquake happens offshore, the waves from that earthquake, which is a movement, is about 5 kilometers per second. But the seismometers close to where the epicenter is, where the rupture happened, will know it within, say, a second, and that is relayed all the way across Japan. So they have time to turn off, say, the bullet trains. They get this few seconds warning, but because light travels much faster than waves through the earth, those few seconds are very precious, and it allows a lot of things to be shut down, okay, avoiding damage.
That gives me some hope, but I'm not hopeful about the pattern, because you said 1,000, 1,500, and right? That's what you said. In this area, you said that seems like there's one to come.
Well, one might argue there was one 20 years ago in the northern part of the Gulf, a magnitude 7.3. But I mean, these, what we think, we don't know, for example, at the location of the King Salman Bridge that is upcoming, we don't know when the last major earthquake was there.
Got it.
And maybe it was the 1588, and therefore it's probably getting closer to the next big one.
You wanted to add?
No, just I wanted to add, it's mathematically it's much easier to predict a smooth signal than a varying signal, especially extremes. You can show this mathematically that it will be very uncertain if you want to predict something that is changing suddenly. But this is one of the reasons. But the second reason, the time scale of the earthquake is so long. You can say it will happen, but when it will happen, then to predict exactly,
and
it's
more
something very
and more
difficult.
people are looking at these combined effects. So, I mean, you have big volcanic eruptions; they affect the climate, you have the oceans, and then you have the other way around. For example, in Iceland, at the end of the ice age, you had all the ice melting away, and then following, there were many more volcanic eruptions. And now, with the glaciers melting away in Iceland, the volcanic eruption frequency is increasing. It is increasing. So there's a lot of these kind of feedback. Also with groundwater pressure, you inject water,
system.
you trigger earthquakes.
It's one Earth.
It's one greater system.
Michael?
Just wondering if you guys have a favorite earthquake or volcano movie. Are there any good ones? Anything factual to take away from those, or or anything like that?
That is a fantastic question. I'm going to document that as possibly the best question I have received at a Sci-Café. So please, take your pick.
There's plenty of stuff on YouTube. Okay.
Are you thinking of any in particular, Michael?
I'm just seeing some of the Hollywood.
Yeah, no, I'm still waiting. I think I'm still waiting for my favorite one in that respect. I mean, there have been, to make it dramatic enough, things go a bit wild in these movies, and there could be, we always think about, okay, there should be more references to the real science, because there's still quite dramatic, but for Hollywood it's not dramatic enough, so they have to say, oh, it's a magnitude 10.5 earthquake, which cannot happen. And so no, I don't have yet. So, but I'm happy to collaborate with some director with, I know some dramatic things that I can put in.
But I mean, nature itself creates enough drama by itself. If you go on YouTube and look for footage of the 1980 Mount St. Helens eruption, that's not it's actually, there's no live movie, but there's a sequence of photos done that were shot by someone at the U.S. Geological Survey. And you can see the volcano bulging from one side, and then you see the landslide that triggered the blast. That by itself is quite dramatic.
I think we need to figure out how to finance this movie. Got time for maybe one more question. Yeah, Siggy? She's coming.
Yes, I wanted to continue with the earthquakes. Is there a possibility of triggering earthquakes? So, like you trigger avalanches, to prevent damage. Is there a possibility of putting explosives or something?
There are documented cases where, for example, actually in what is called enhanced geothermal energy, like the Sulz project in Switzerland, they were pumping water down several kilometers deep into fractures and then flowing it back to get the energy out of it. And they triggered earthquakes. So small earthquakes, but they were felt. Magnitude, say 3 to 4, can barely be felt, but it made everybody uneasy, so they shut down the project. And big earthquakes also trigger smaller earthquakes in nearby faults. I think they had a magnitude 9. I think the highest magnitude earthquake was a 9 in Chile, and that triggered earthquakes elsewhere in South America, and actually the whole planet was ringing like a bell for a while, because it's wave ringing is basically wave motion, but it's not the energy from a rupture or an earthquake is attenuated quite rapidly. So the big shaking, which can exceed 1 G, which is 10 meters per second square, dies away quickly as you get away from the epicenter.
Yeah, I guess the question also was related, can we do something to advance the next earthquake so it comes sooner and becomes smaller than if it would be occurring 20 years later when more stresses have accumulated? And people have thought about these things. What can we do to advance major earthquake on the San Andreas faults, for example? And I mean, I guess the most effective method that we know today, instead of putting down a nuclear blast or something, is to just increase the groundwater pressure you pump in. And a great example of this effect is seen now all over the Midwest in the US. In Oklahoma is becoming the earthquake state of the United States, because through fracking they are triggering so many earthquakes. And the question would be, okay, how large of an earthquake can you trigger with a water injection when you pump water into the ground? And this, one would say, many people believe, well, there is no upper limit. If you have a fault that is more or less ready to go and you just kind of push it over the edge, then you could actually produce a very large earthquake. Other people say, no, we can't produce bigger than magnitude 4 or 5s with this. But this is, But I think you would never get an agreement in the state of California. Okay, let's try to produce the next big earthquake before it becomes too large, because it would be very quickly an insurance nightmare, I think.
All right, time for one more question. One more question. Yeah, at the back there. Microphone's coming.
Question to expert. Do you think ocean atmosphere system can trigger the earthquakes?
Yes, we are seeing increasingly influence of the atmosphere and groundwater and the oceans on earthquake activity. Not maybe on and off, but showing modulations. And people have, for example, looked at California again, how the drought over the last decade or so is influencing earthquake activity. How so? Well, what happens is people are pumping out water in the Central Valley of California, reducing basically mass. So you're reducing mass. There is less water in less groundwater around, and this kind of relieves pressure on the. You can actually see it. The land moves up a few centimeters, and this has an effect of an earthquake activity. It modulates it. It doesn't control it. I mean, the earthquakes are going to happen still. This is also seen in the Himalayas, where the monsoon is dumping a lot of water, putting load on various parts on the Ganges Plain and also up in the Himalayas. And you see modulations of earthquake activity due to these large mass changes. So this is a clear interaction between the ocean atmosphere system and earthquake activity. So it's kind of advancing earthquakes or reducing earthquake activity a little bit, but it's not the driving engine. That's still tectonics in most places.
I think with that, we'll call it a day. I do want to point out, I think this is a field that we don't publicize a whole lot here at KAUST. I think it's an important field. Hopefully you got a sense of it today. And I would just like to point out in particular, these developments along the coast of the Red Sea, projects that KAUST is involved in. I mean, saving 2 billion rials in King Abdullah Economic City, maybe being a part of the King Salman Bridge and the construction there. I think KAUST is engaged in some very important science, some very important and applied research. So thank you for joining the Sci-Café today. Please thank the panelists, and we will see you next time.